Hi, everybody. Today we are talking about tension and how tension is going to play a role in our force problems. So we start off with a traffic light. A stoplight hangs as shown and remains at rest. So why are there tension in the ropes? So let's talk about what tension does, right? So tension connects two objects, uh, and it usually represents a Newton's third law pair, right? As one object pulls harder on the rope, there is a greater tension force on the other object, and that other object must pull harder to oppose that motion, right? So the tension here is due to gravity. A lot of the tensions that we'll talk about are due to gravity, usually mass hanging off a table with a pulley or some kind like that. So the tension in this problem is due to gravity pulling on that stoplight. Tension 3 holds all the weight and it connects at that knot there, right there. And then tension 1 and 2 divide that force between them. So what is the net force acting on the stoplight? So we can know this right off the bat because of this hint we got here, right? It remains at rest. So since we know that the stoplight remains at rest, we know that the net force acting on the object must be zero, right? An object at rest stays at rest unless acted upon by unbalanced forces. And since there are no since there is no acceleration here, there are no unbalanced forces. So net force is zero. Now, next, let's map out two strategies for finding the tension in the rope. So if we look at this problem, okay, you can do one strategy, which is divide this into x and y coordinates. So you've got the x, you've got the y, right? Then you can say, here is your theta 2, and then there is your theta 1. So we can see that, whoops, that's theta 2. We can see using geometry that we would split these into their x and y components. The y components of T1 and T2 would balance T3, and then the x component of T2 would balance the x component of T1 to make everything nice and neat, hunky-dory. Okay, another way to do this problem is law of sines. So what you do is you take those lengths and you recreate them in a triangle. So we know that T3 is vertical already. T2 comes off at an angle. So we could say that this was T2. And then T1 comes down in the other direction. You can say that's T1. And then we would have to figure out our angles all throughout the triangle, make sure they add up to 180 total, right? And then law of sines, you can write it two different ways. There's either A sine A equals B over sine B equals C over sine C. Or if it's more convenient to have the sines on top, yada, 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 that is also allowed as well. If the ABC is on top, or if the sine A, sine B, sine C is on top, as long as you're consistent throughout the equation, it doesn't matter because the ratio is what's important in that problem. So that's law of sines. What you would do is you would look at this triangle and label these as A, B, and C. And then the angles A, B, and C must be opposite of the length. So angle A is opposite A, angle B is opposite leg B, and angle C is opposite leg C, right? So that's how you can do this problem. You got two different strategies that you can go for. Now, if we go to the next slide, let's just solve this problem. They give us some values. We can solve it, right? So the stoplight weighs 200 newtons. So that tells us right off the bat, T3 equals 200 newtons. Angles 1 and 2 are 25 and 18 respectively. So theta 2 is 25 degrees. Theta 2 is 18 degrees. And then we just need to calculate tension. So what we'll do first, we'll do both strategies just so you guys can see how this works. So let's split this up into our summation of forces. Let's look in the x first. Okay, so I'm going to redraw the x coordinates that we had here, or I guess the axes, not coordinates. Okay, so here is our theta 2. Here is our theta 1. So now, as we come back over, we can see the geometry that we need to use. So we'll have the right be positive and the up be positive on this coordinate system. So we'll start with T2. The x will be cosine theta 2 minus T1 cosine, what's happening? There we go, theta 1. And that will all equal 0 because there is no acceleration, right? Now we have summation of forces in the y. So up will be positive, so that means the T1 and T2 components will be positive. You have T1 sine of theta 1 plus T2 sine of theta 2 minus T3. That will all equal 0 as well. Now, we have theta 1 and theta 2, so all that trig, that's just calculator work, but we don't actually need to worry about it because once we get to the end, we can just plug those into the calculator, not an issue. T1 and T2 are the issue. T3, again, not an issue. We know the stoplight weighs 200 and T3 must support the entire weight of the stoplight. So what we have here is we have two equations and two unknowns. If we solve, let's see, if we solve the top one, right, we can say that T2 cosine theta, you know what, I'm going to do this down below on my extra slide. T2 cosine theta 2 can equal T1 cosine theta 1. Then the other equation, we have T3 equals T1 sine theta 1 plus T2 sine theta 2. Right, let's double check. And that is right. Okay, so we have two equations, two unknowns. We have T1 is unknown, T2 is unknown. So what we'll do is we'll solve one equation for one of the unknowns, then plug that back in. So you always want to solve for the more simple equation so that you're not plugging in a mess. That's my take anyway. So let's solve for T1. If we take T2 cosine theta 2 divided by cosine theta 1, that equals T1. The thetas are different, so those cosines don't cancel. Then we take that T1, we'll substitute it in right there. So then we have T3 equals T2 cosine theta 2 divided by cosine theta 1. And that is all times sine of theta 1. You guys can already see there's a tangent coming out of that one, right? And then we have plus T2 sine theta 2, right? Now the only unknown in that equation is T2, right? So let's start simplifying, see what we can do from here. Got T3 equals T2, let's say that's cosine theta 2, then sine over cosine is tangent, so we can say that is tangent theta 1 plus T2 sine theta 2. Now we have two T2s, but there's a lot of trig in the way. So this can commonly freak out students. What are you supposed to do, right? If you divide by that sine theta 2, that doesn't help your cosine tangent. If you divide by cosine tangent, that doesn't help your sine. So what you need to do is factor out T2 to make this simple. T3 equals T2 times cosine theta 2 tangent theta 1 plus sine theta 2. Then you divide all that over. Let's see if I can just move it. That'd be kind of cool. I can. Oh, that's so neat. All right. So then T3 divided by all that mess equals T2. Okay. And no, we're not going to substitute all that over because, again, that's a mess. We have T3, we have all the thetas. Let's just evaluate that. You get 266 abouts newtons. Okay, so that is tangent 2. Sorry, not tangent, tension 2. Then we'll just bring that over and plug that into our tension 1. If we take 266 times cosine theta 2 divided by cosine theta 1, that will give us T1. And remember, theta 1 is 25, theta 2 is 18. We were given that. So 266 cosine 18 divided by cosine 25. You get 279. So T1 equals 279 newtons. Okay. So that is the X and Y method of solving this equation, okay, or this problem. Now let's show you the law of sines method of doing this problem. So what we need to do is we need to make our triangle, right? I'm going to zoom in so I can do this a little bit more exact. So we have our T3 is completely vertical, right? T2 comes off in this direction. T1 in this direction, right? Now, if we look at the thetas that we were given, right? If we look over here at our diagram, right, the thetas are given at the top of the angle. So if this were tension 1, this would be angle theta 1, and this would be angle theta 2. So what can we do to get all of the angles in this triangle? Well, up top here, this makes a 90-degree angle, right? That's 90 degrees. And then if we have this here, this also makes 90 degrees, right? So we can use the 90 minus theta whatever method. So this will be 90 minus theta 1. This right here, that is 90 minus theta 1. And here, if we use geometry methods there, that must be theta 2. So this would be 90 minus theta 2. Then using the same geometry methods, that would be theta 1. So this would be theta 1 plus theta 2 to get that angle there. Now, that gets kind of messy, right? So because now we need to look at what is A, B, and C. So I'm going to arbitrarily call this A, this B, and this C for our angles. So angle A equals 90 minus theta 1. Theta 1 is 25, so we have an angle of 65 degrees. Angle B is theta 1 plus theta 2, which is 25 plus 18, so you get 43 degrees. And then angle C, we have 90 minus 18, that comes out to 72 degrees, right? Now, we also know what sides we're looking at. That means that T2 is A, T3 is B, and then T1 is C, just by looking at what's opposite of each length, right? So it's easier if we use the method where we have A over sine A equals B over sine B equals C over sine C, right? And we know the entirety of B, right, because we have T3. So T3, we have 200 divided by sine 43. Okay, and that will equal T1 divided by sine 72, which will also equal T2 divided by, let's see, angle A, sine 65. Okay, so now you just need to multiply over. So let's solve this first, right? So if we solve this, we have 200 sine 72 divided by sine 43. That would equal T1. So let's prove that we're pretty close to what we had before. That gives us 279 newtons. Now, what you can do is solve this equaling this, right? So then to find that, we have 200, multiply your sine 65 over, divided by sine 43, that gives you T2. And T2, if we do that, let's see, we have sine 65, that gives you 266. Here we go. Okay, so both methods are going to work on that. Now you can see that law of sines didn't take as much work, or I guess much space, really. It didn't take as much space. But depending on which method works for you is also going to work for the problem. It doesn't actually matter which method you do, as long as you do the method you're good at. Because when you run into this on a test, you're racing against the clock. Whichever one you're good at, stick to it. Whichever one you're fastest, do it. Because like we just showed, the problem works no matter which one you use. All right, now let's talk about tension and these kind of like a Newton's third law discussion. Okay, so let's start with on the left, let's compare tension A and tension B. So there is a rope connecting these blocks. One rope connects block 2 to block 1. One rope is pulling block 1 to the right. So if we look at tension A, right, we will look at the summation of forces for A. Okay, we have tension A equals the mass times the acceleration. But we are pulling mass 1 and mass 2 as we accelerate the system, right? So that is responsible for pulling both masses, assuming frictionless surface and weightless rope, right? Because then we'd have to pull the mass of the length of the rope for section B. But massless rope, or I guess weightless rope, and frictionless surface. Now, if we look at the summation of forces for part B, we have tension B is only pulling the mass 2. So even though this rope is being pulled in the right direction, tension A and tension B are not going to be the same because they're not actually pulling the same masses. So tension A is actually greater than tension B because it's pulling both masses, while tension B only pulls one mass. So the tensions can actually be different in a problem like that. Now let's compare the force M1 exerts on M2 with the force that's actually pushing M1, right? So let's say my hand is pushing M1, right? That is called force F. Okay? And that will that's pushing M1 and M2, and it is accelerating them, right? Accelerating the system. Now let's look at the force that one is exerting on 2. Now you'll see this notation, F12. You'll see that notation system often in physics problems, in my videos, in textbooks. They use this often. I wish they would put a comma or a dash between those because when I look at it, it looks like F12 to me. sometimes when you have, say this is a mass of 7 and a mass of 3, the force that the 7 block is exerting on 3 could be shown as F73. And then if we look the other way, this could be F37. Not the best notation that we have, but it is very common in physics to use this kind of notation. So I won't change it just for the sake of my videos, because you will run into this as you do your physics. So the force exerted by 1 on 2, right? I am only pushing with my hand 1 block. It just so happens there is another block on the other side, right? So I'm pushing both masses. But the force that M exerts on 1, M's not having to push itself, right? That is not accounted for in that force. So this is really just pushing M2 times the acceleration. So, and then if we looked at in the opposite direction, F21, the force that 2 puts on 1, that would be the opposite, right? So then you would have negative M2A, right? Because that is a Newton's third law pair. So this is a common notation that you will run into. Just a heads up, that I'm not talking about F12. 12 didn't come out of nowhere. That is the force that 1 exerts on 2, and below the force that 2 exerts on 1. Okay? So this slide is really just to demonstrate that you may need to look differently when we have multiple objects in a problem, because the forces between them may not be as simple as they seem. Okay, now speaking of things that are not as simple as they seem, we have a pulley on a table. M1 is attached to M2 via a weightless string, and that weightless string is over a weightless, frictionless pulley. Okay, so let's read the problem. 5 kilogram mass is M2. It hangs from a string that passes over a weightless, frictionless pulley and is joined at its other end to a 12 kilogram block M1, which lies on a frictionless table. Now, why is the word frictionless used twice? Well, that's very important. First, here we have a frictionless pulley. We haven't even gotten into how to calculate friction. And unless someone just gives us this pulley has 50 newtons of friction, it's kind of difficult to calculate the friction inside of a moving object. So we haven't even gotten to that yet. And we also have not started the fun equation yet. That'll be in our next video, about how to calculate the friction on a surface between 2 objects that are rubbing against each other. So we haven't even gotten into friction yet. So that's really important, that this is all frictionless. Next, why does the pulley's weight matter? So we also have a weightless pulley. Very important, because that pulley actually has mass in real life, right? In reality, that pulley has mass, and it actually takes some effort to actually rotate something that has mass. Whether there's a lot of friction in those bearings or not to cause it to rotate, it still takes effort and force to cause something to start rotating. And when we look at rotating objects that have mass, we will call that moment of inertia. But that's something that we will go over much later in the course. So let's start off with a free body diagram for each block. M1 has a normal force opposing mg, and then it has tension pulling M1 across the table, right? Then we have M2 that has M2g, and the only thing opposing its motion is tension pulling up, right? Now, those are the free body diagrams that we're going to use for this problem. Next, we are going to calculate the acceleration in terms of m, g, and theta, and then we'll answer the question, why is it not simply g? So let's go back down to our free body diagrams, and let's solve these for acceleration, right? Yeah. So there is no acceleration for m1 in the y direction, right? It's sitting on a table. It's not moving vertically. It's moving horizontally. So we'll disregard that. So if we do the summation of forces in the x, we get tension is the only positive, and that equals mass times acceleration of the system. Oh, that equals m1 times acceleration of the system. You got to remember that. Then over here we have this summation of forces. There is only acceleration in the y, and it's the same acceleration that we had there. Now, this is something that we're going to have to do when you're doing pulleys. Mr. Askey calls it melting the axis. I just say that you're going to continue the either direction of motion or continue the acceleration. But the acceleration of that m1 is horizontal, right? That is going towards the pulley. Then that pulley is now causing m2 to accelerate downward. So the direction of that acceleration needs to stay positive throughout the entire problem. If you start flip-flopping those directions, then you're going to have a positive negative issue. So since m1 towards the pulley is positive, we have to say that m2 down is also positive. So in this case, the summation of forces, m2g is positive and tension is negative, and that will equal m2a. And the a will stay the same. There is no acceleration in the x or acceleration in the y. It's the acceleration of the system. Okay, now let's solve for acceleration, right? Is that what we're solving for acceleration. So over here we have tension divided by m1 equals acceleration. No, that's not what we want to do. We'll solve for tension and substitute that in. All right, so tension is already m1a. So let's put that over here. m2g minus m1a equals m2a. Very commonly in a tension problem, can you eliminate tension altogether? Now we have, let's move the m1a to the other side and isolate our a. So we have m2g equals m2a, m1a plus m2a. Factor out your m's, so you have m2g equals m1 plus m2, all multiplied by a, and then you divide that over. m2g divided by m1 plus m2 equals acceleration. Now, why is that not just m2g? Or I'm sorry, why is that not simply g, right? So the acceleration, you would think, since it's all frictionless, the m1 is just going to slide right towards the pulley. You would think that the acceleration should be g, because the only acceleration is m2g, right? It's just being pulled downward. So why is acceleration not g? Well, if we look at this, right, we have this ratio of m2 plus the sum of masses times g. So we have to take into account that these objects do have inertia, right? They do have mass, and they are going to resist that acceleration. So if there was no other block, then we would have an acceleration similar to g, right? You would have m2g pulling down, tension pulling up. But if there was no mass on the other side of that, then there would be no tension, and then you just have m2g straight down, right? And then your acceleration would be g. Now here we have a ratio, m2 divided by the summation of masses. Now let's give these, oh no, they do have mass, don't they? 12 and 5. So that means that this was really 5/17 g, right? So you have a ratio. It's not completely g. It's 5/17 of g. And that is going to mean that we're accelerating not at g, but as a fraction of g. And that fraction directly correlates to the masses that are being pulled because they have inertia. They're going to resist that pull. Okay, so that is why, if we come up here, why the acceleration is not simply g, because there are multiple masses being moved all by one force of gravity. All right, last problem. A pulley on an incline. Okay. Now it asks first, what is the driving force in this situation? So we have M2 being accelerated down the incline, and then we have M1 being accelerated up the ramp, right? You can see that there with those acceleration arrows. So A, that driving force is going to be the gravity on M2. Now, what is the resisting force? Well, we're probably assuming friction, right? We haven't done friction yet. So the only resisting force would be the gravity acting on M1. So it is really gravity resisting gravity, right? Whichever mass is going to have the stronger weight is going to win. Now, C, derive an expression for the magnitude of the acceleration in terms of M1, M2, G, and theta. So what we'll do is we will start with a free body diagram for both of them. So we have the incline, right? Let's not draw the incline. We'll start with M1. We have tension and M1G. Tension and M1G, right? Then over here, we have M2. Now we have M2G. Then we have a normal force coming off the incline, right, at an angle, because the contact is at an angle. It is not pushing directly up. And then we have the tension pulling us back, right? Now, when we're working with an incline, it is best to use a coordinate system that lines up with that incline. Okay? So that means that the theta that is on the incline in the picture, this theta here, that theta will be right there. Okay? So that means that if we do summation of forces in the x, which is where the acceleration is on this tilted axis, right? Then we have M2G, but we want the x, so that would be this right here, right? So that would be opposite of theta, so that would M2G sine theta minus the tension force, and that would give you M2 times the acceleration. Now, there is no acceleration in the y for this problem, but you could see that it'd be normal balancing with M2G cosine theta, right? Because that would be right there. That would be adjacent. Now, if we do the summation of forces in the y on this side, you would have the tension force minus M1G equals M1A. Now notice that the positives are a little different, right? Our positive is going up here. That is positive. Our positive on M2 is going down the incline here. And remember, this is us melting that x-axis, not x-axis, sorry, melting the axis over that pulley because we need to keep the acceleration positive in every scenario of this system. So we want to derive an expression for acceleration. So let's solve for tension over here. and we will substitute it in. Like I said before, solving for tension on these problems gets rid of that unnecessary variable. It's not even in the list of variables we're supposed to use. So, and it also allows us to have these two equations, two unknowns kind of situation, so we can get everything lined up. Now, another way that we can do this would work on the previous problem as well, but I will show you this method also. What you can do is you can add the summation of forces. So if we take T minus M1G equals M1A, and we add these together, the tensions will cancel, and you would get M2G minus M1G equals M1 plus M2 all times A, right? So we have this right here. You can see how that can become this here. And you can see that, like we were talking about before, the driving force in this problem is M2G. The resisting force in this problem is M1G, like we discussed before. Now, if we want to solve for acceleration, you just divide that over, and you have M2G minus M1G all over. Actually, you know what? Before we do that, let's pretty that up. Say we have G times M2 minus M1 divided by M1 plus M2. Okay. And that would be acceleration. So this is a little different than the problem before because it's a different scenario, because now we have an incline, right? But now we can see again, acceleration is not G, it's going to be G multiplied by a ratio of those masses, right? And M2 must be greater than M1 for this to work, obviously, because as we can see, M2 is winning that battle. And we can see that here in this math. Right here, if M2 must be greater than M1, or all of a sudden everything goes negative, right? But since M2 is greater than M1, this ratio will be a positive number, and then we have a positive acceleration. Okay, that's all for our tension video. Our next video is going to launch us into a series of videos where we talk all about friction.